person is recording or not. So.
Yep.
Okay, it's, we're at the half hour, so we can go ahead and get started. So first, thank you everyone very much for coming to this tutorial today. We're very glad to have you. So we're first just going to introduce your instructor team for today. So I'm Matthew Feickert. I'm a research scientist at the University of Wisconsin-Madison Data Science Institute. And so I'm not a Pixi expert per se, but I'm kind of an enthusiast, as well as for my research, I end up using a lot of GPUs for different data science and machine learning applications. So CUDA is something that I have to work with a lot, but I'll now also let my co-authors and co-presenters introduce themselves, as they are experts.
Sure. Oh, yep. Hi, I'm John Kirkham. I work at NVIDIA. Previously, I've worked at HHMI, which is like a nonprofit that does like neuroscience research and that kind of thing. And I have a long history in the Conda Forge community. I've been working on Conda packaging of CUDA packages.
Hey, and I'm Ruben Arts. I am on the Pixie team itself, on the core team. I work for Prefix, and we're basically here to try and solve the reproducible problem within package management through the Conda ecosystem. So together, this team kind of resembles the title of this presentation. And we hope to let you learn a lot of new things about using Pixie in the machine learning ecosystem. I think I can give you the word for the introduction.
Yeah. So before we kind of get started with getting into making sure everyone is set up correctly, we're also going to just kind of go through some quick slide things. So as was mentioned, this is this workshop. So you hopefully already have found that there's Wi-Fi, but if you haven't, there's a public Wi-Fi network here that you should just go ahead and connect to. There's no password, so you can just join. Also, as mentioned, if you've joined the SciPy 2025 Slack, which hopefully you have, then there'll be this Slack channel that is made for the tutorial. It's just tutorial and then the name of the tutorial itself. If we drop out into Slack for a second, you can see that there's at least 13 people who have already joined that Slack channel. I'd encourage everyone to go ahead and join that, so that way we can both be monitoring for questions later on in the week, and then also we can share links here as needed. The website that we're going to be working from is linked there, and then also there's setup instructions that are linked there as well. We'll go ahead and go through those in a little bit. And we'll come back to this later on, but today we're going to be using a resource to make sure that everyone has access to NVIDIA GPUs that have, so that we can do some CUDA accelerated workflows. The NVIDIA Brev team was kind enough to go ahead and donate cloud credits for everyone to be able to use these today. So we're going to use the code later on that we'll go through, which is SciPy Summer 25. You can take photos of this right now. This will be useful for today, but we'll go ahead and come back to this when we actually need to get into the filling this bit out for the billing information. Also, a special thank you to Carol for kind of helping facilitate all this. It's very much appreciated. Right, so I think with that, that's maybe enough of the quick logistics. So we're now going to go ahead and get started with actually just making sure everyone is set up correctly. So the way that we're going to do this is to make sure that you get to the tutorial website. And if you haven't found it yet, by linking to it either on the pre-talks or one of the other areas, if you just go to www.github.com/mattfeickert-talks, so github.com Matthew Feickert-talks. Then you'll see that the very first pinned repository is the repository that for this tutorial. And if we click there, then there's a linked, the linked website that actually is the tutorial itself, which drops us in kind of at the overview page, and the setup instructions are right over here, the very first item to the left. Okay, so before we go any further, can I see a show of hands of people who have not been able to find the tutorial webpage? Okay, everyone's found it, I believe, so that's grand. Okay, so we're gonna, you should have already received an email with setup instructions, but we're going to try and lightning talk speed, try and make sure that everyone is at the same spot so we can make sure everyone is good to go. So you'll notice that this is just kind of outlining all the resources that you will need to try and run this tutorial. It's mentioned that to get the most benefit, you're going to want an NVIDIA GPU, and so as mentioned, we have Brev resources to make sure that everyone has access to one, regardless of if you have one in your local laptop or not. The very first, and we also have this kind of outline of the software that's required. You are going to be needing to run a 64-bit version of either Linux, Mac OS, or Windows, and so if you are trying to run this right now on a Windows tablet, you might have some issues, but it looks just from looking around the room that everyone should be in good shape. We're also going to use Pixie, Git, the Brev command line interface, and then we're also optionally you can also use a text editor of your choice, so it's something maybe like Visual Studio Code. And later on at the very end, we're also going to be using, as we go along, one of the goals for this workshop, or this tutorial, is to make sure that people leave with not only having run some commands and learn stuff, but also having a GitHub repository that is kind of an instantiation of the knowledge that you learned today. So we'd like to also ask you to make sure that you have a personal GitHub account so that you can create a repository as we go. Yeah, I'll skip the GitHub 2FA thing. So the very first thing that we're going to do is we're going to install Pixie together. So if you are on a Unix machine, you simply just need to run this curl command, and if you're on Windows PowerShell, then you can use this PowerShell command. So I'm just going to copy and paste this. I already have Pixie installed, but this would, I already have Pixie installed, but this won't hurt to just run it again. It will just tell me that I already have everything installed.
No, it will actually install.
Oh, okay.
The curl is not that smart.
Yeah. Okay, well, it seems that the Wi-Fi is maybe a little slow, so I'm going to cancel it out, but you should have already gotten there as well. If you, so the next thing you're going to need to do, though, is you're going to, once you've run that curl command or that PowerShell command, you need to make sure you either restart your shell. So you either need to open up a new tab in your terminal, or you can simply, if you're in like the bash shell, for example, you can just source your bash RC file, and that should refresh your session. And so you should now be good to go. So everyone should be able to now type pixi-help, and you should get output. So can I see a show of hands of anyone who doesn't have Pixie installed at this point? Oh, we have maybe one? Can one of you guys go? Okay, I think maybe we're good then. Okay. So the next thing we're going to do is we're going to make sure everyone has Git, because as mentioned, we're going to do some version control work. Most of you probably already have Git controlled on your Git installed on your machine, but you can test this by either typing wishgit or command-vgit. But if you don't, then you can simply install it with Pixie. So you can do Pixie global install Git and hit enter. And I already have it installed, so it immediately just tells that to me. But if you don't have it installed, then it will get Git from Conda Forge and make it globally accessible to you anywhere on your machine. And then we also would recommend, if you aren't already familiar with the Git command line interface, then GitHub provides a GitHub CLI that can be a little bit useful. So we'd also recommend that you run pixi global install gh. That will also make the GitHub command line interface accessible. We are now also going to ask that you install also using the pixi global command Brev, and we'll get into Brev in a little bit now. So we're going to do pixi global install Brev. This is only going to work if you're on a Unix machine, and so if you are using a Windows machine, we are going to ask that you do everything inside of the Windows terminal for inside of WSL2. Can I see a show of hands of people who have a Windows machine who do not have WSL2 installed or don't know what that is? Okay. So we'll go ahead and help get you set up. And then the other thing we're going to do is mention we're going to want to make sure you have a personal GitHub repository. And we're actually now going to make sure that we're all on the same page. We're going to create a repository for everyone that's called Reproducible ML SciPy 2025. To make sure that everyone is able to do this and we're all on the same page, we're going to use this GitHub command line interface command to do it from the command line instead of going into your account and doing it manually. So we're just going to use this copy and paste button that's right here. So copy that into your clipboard, come back to your terminal, paste it in, and hit enter. And this will now, okay, so this has now created this repository on my personal GitHub account. So if I open that, then I see that this exists on my personal GitHub. But then we also see that it's cloned this locally onto my machine. And so now I can do change directory into this reproducible ML SciPy 2025. And I see that there's this license and repo, so we are good to go. All right. So now what we're going to do is Brev is this, provides you this ability to provision cloud resources that use NVIDIA GPUs. And so the very first thing that we're going to do is make sure that everyone has a Brev account. You hopefully have already done this, but if not, then we're going to have everyone visit this login.brevnvidia.com sign-in and go ahead and fill out this information. So here you're going to need to enter in your whatever email you want to use. I need to actually look up what I used. Okay, I used my work email. And then you're going to just need to agree to terms and conditions. You'll sign in. If you haven't already created an account, then you'll be prompted to go through those steps. We're now seeing that I need to enter my password. And then also there's multi-factor authentication. Okay, so we are now logged into the account, which is good. So we've gone ahead and created the account, but we now want to make sure, so first of all, can I see a raise of hands of people who did not have an account created and are kind of in that step? Okay, so we have a few people, so we'll, so I hopefully, if anyone is having issues, please go ahead and raise your hand and make some noise. But I anticipate that it'll take people just a few minutes to kind of get caught up. But the good news is we aren't going to be using Brev right away. We're just going to make sure that we provision some resources to go ahead and get going. So when we get back to it, everything will be ready. So if you aren't caught up right now, that's going to be okay. For those. For everyone who basically is at that point and has Brev installed, we're now going to make sure that we can actually access Brev from the command line. So we're going to run Brev login from the command line. And so it's going to prompt us if you've never done this before, it will ask for the email address that's associated with your account. And then if you type that in, then it will go ahead and give you an authentication link. And it will, if you just hit enter again, that will open up in your browser. And it will then have you go through that same login process. That's just making sure that you actually authenticate locally on your machine versus up in the cloud. So you're going to have to log in once more, but that's all fine. You'll just be returned to the exact same page that we were previously on, but this now means that you've gone ahead and done authentication. All right, so for this workshop, we are going to be using cloud credits that were given to us by the NVIDIA Brev team, and we're going to be using those to configure one particular instance of Brev, and so that's going to be using one NVIDIA L4 GPU with 24 gigs of VRAM, and then also 16 gigs of RAM for CPUs. It was on Google GCP. But the way that we're going to do this is to make sure that you don't, if you don't, since this is going to actually use resources, if you don't have any billing information provided, then it won't go ahead and let you provision anything. So we're going to do this by logging into the website, and then at the top there is this billing section. If you go there, then there is going to be a redeem code bit here. So you're going to hit redeem code, and then here you are going to enter the code that we have, and that's again SciPy Summer 2025, but I'm going to also paste that into the Slack. So if you've joined the Slack, I'm going to say, hey channel, the code is SciPy Summer 2025. Yes, send it. So you should be able to, you should now paste in SciPy-Summer 2025 and hit redeem. I'm not going to hit redeem just because those are a code for you. I already have credits going. So that should then update your billing information, and everyone should then make sure that will give you at least 4 hours of runtime today. We're going to see if we can maybe extend that a little bit more. But to make sure that everyone creates the correct partition, once you've gone ahead and added that billing information, we're now going to come back to the setup instructions, and you can specify what instance you want from the command line. So we're going to copy this brev create pixi CUDA, which is the name of the instance that we're going to call it today, and then we're going to request this particular GPU instance. So we're going to copy that to the clipboard, and we're going to come back to the command line, and we're now going to copy and paste that in and hit enter, and we now see that things are spinning up. And so, yeah, so it's going to take a little bit of time to get going, but if you see this, then that means that things are getting spun up correctly. We'll then come back later on. For now, we are going to, we basically reached the end of the setup until we come back and actually are going to log into Brev at the end of the Pixie introduction. So we can now kind of move on with the actual material. And we're going to now, so since we've reached the bottom of the setup, the next section is the introduction. So we're going to click here, and we're going to do a very quick overview about what this tutorial is and what it isn't. So I'll first say this is not a tutorial that is going to teach you state-of-the-art machine learning techniques. So if you came here today to learn about that, I will not be offended if you get up and leave, and I'll instead recommend that you go to either Hugo or Eric's tutorials tomorrow, where you will learn about that sort of stuff. Hugo's in the back of the room, so is Eric. Wave your hands, say hi. Yeah. What we are going to be talking about in this tutorial is how we as scientific researchers and people trying to do data science can create really complex computational software environments that might contain many different dependencies, potentially conflicting ones that can also leverage the great hardware acceleration that comes from the CUDA stack, but also be able to do this in a reproducible way where we don't have to become, hyper experts in some form of like engineering. Maybe you're a researcher and you just want things to work. So what we're going to talk about today is how Pixie enables you, along with the CUDA stack from Conda Forge, to be able to do this at a very high level using semantics that I would say make sense from a researcher's goals and perspectives. I should close Signal so I don't get my group chat. So I would also make the argument that we live in a really complex, that modern scientific workflows are complex. They require many different forms of software. It's now very common for a researcher to be working not in a single language, but across many different languages and different computational stacks across heterogeneous computing resources as well. So it might be that you start off with a data science workflow on your laptop, but then as things scale up, you want to be able to move to either your testing cluster or your research, or if you're a researcher in a lab, you might have a deep learning machine, or you might be scaling up across a whole distributed set of cyber infrastructure. We want to make sure that these pieces of software work everywhere and that we're able to not have to design one brittle bespoke environment for one and have to build a totally different environment for another. So for time, I'm going to kind of skip this little bit here, but you can, as a self-exercise, you can think about what are challenges to reproducible research in general. I'll just kind of mention, a few that, you might have software packages that are not, that are complex. They might not be well packaged. You might also suffer from reproducible building of different things, or you might not actually have your data somewhere that's accessible, and you might not have your analysis code under version control. These are all difficulties that you might run into, but we can at least try and make sure that if you're dealing with software environments, you know and understand what the environments that you have, and that you can manipulate them in a declarative fashion and get hash level reproducibility. We're today talking about the concept of reproducibility of software environments, though. We're not talking about reproducibility of computations. You can imagine that even if you have the exact same software environment, that you could run computations from one run to another, and they could differ. They can differ because of floating point precision. That's not infinite precision. It's only down to a certain level. Also, order of operations might not be reproducible if you're running multi-threaded applications. So we're not going to be talking about how can you get bit-for-bit reproducible results. We're going to be talking about how can you be sure that you have the exact same software environment every single time you run your code. We're going to leave the burden of actually determining what level of reproducible results up to you, the individual researchers. Right, but as was mentioned, we also care about, given that machine learning and accelerated data science stacks are more and more becoming kind of a bread and butter part of academic research as well as data science and industry, we want to also be thinking about how can we make these workflows accessible and reproducible on GPUs so that we can take advantage of all this great work. So GPUs can also kind of be their own beast. If you've ever in the past had tried to set up a GPU environment by yourself, then maybe that was not the most trivial thing of all time. I can personally attest that in 2019, when I was a postdoc, I spent a long time basically setting up my lab's deep learning rig, only for the next update of Ubuntu to break everything. So we're gonna try and make sure that those past versions of ourselves get a little bit of reprieve, and that moving forward we can have things be much easier. So we also want to be thinking about why do we want to do this? We don't want to be make reproducible environments just so we can check some box. We want to make sure that we're doing this so that we can be good collaborators to our future selves as well as to our current collaborators. We want to make sure that we don't have to fight to be able to get the environments and the tools that we want. We want to be able to just say, oh, I have an idea for an experiment. I know I'm going to need these tools. And I can trivially and quickly get those tools on the resources that I need. All right, so I think for time, we're going to move forward, and I've already kind of gone over enough, so hopefully everyone is still here, which means no one has been scared off. So without further ado, I'm going to turn it over to Ruben, who's going to walk us through an introduction to Pixie itself.
Thank you. One question? Yeah. There's a few people where the code is not working.
Which code?
The summer 25.
Okay, maybe we should go talk.
So just a quick note. Some people didn't get the code to work for NVIDIA. Matthew and John are going to figure out if there's something that we can do to help you further. Can I get a show of hands for who it didn't work? That is just 3 until now. Okay, now let's hope they can figure it out. So, thanks Matthew for presenting that part of the tutorial. I think I will try to grow this a little bit more because we're going to go into a little bit more detail. So, first off, what is Pixie? So, some of you probably already have some use cases with package managers before, like pip, like opt, like brew on your Mac, something like that. Pixie is also a package manager. Pixie is a little bit more than a package manager, but in the bare bones idea, it's a package manager that can help you either install things globally on your machine or into a project. And I'm going to go into that project detail a little bit more in this presentation. You have seen the global workflow that Matthew just showed, so hopefully you understand that as well. I want to get a little bit more into what that global installation did. So normally a global installation would be putting files on your system in the same folder, all these projects working together. Pixie does it a little bit differently. So if you have experience with pipx, for instance, where it creates virtual environments for every tool you install, Pixie does the same thing. So if you have Python installed through Pixie Global and another project installed through Pixie Global, these two things will not try to interfere with each other. They're just their own standalone environments. So that might make it really easy to install multiple tools on your system without breaking your system while you're doing that. But continuing, we're going to look at Pixie projects. So what does Pixie solve? Pixie's goal is to create fast, reproducible environments. Mostly developer environments, but you will see that it's much more than just focused on developers because we also want to make it easy for everyone to use these environments and not just the developer group of the team that you're working with. And the problem that we always hear when you're working on some software was like, it worked on my machine. And we want to get rid of that sentence in your daily workflow. So a few of the things that we want to really focus on with building Pixie was reproducibility. So the ability to set up your environment and then kill that machine, start up a new thing and reproduce that same thing. Is that either on your colleague's machine? Is that either on a CPU or GPU that you want to run in the cloud or your CI system? It should just be reproducible without any hassle. Pixie does that through log files. And we'll get to that, what that actually looks like in the next example. Also, speed is very important. Package management shouldn't be limiting you in your daily workflow. So we really focus on building Pixie in a way that you can really depend on that it as fast as possible. For that, we use Rust as the language. Tools like Conda, which Pixie has a lot of stolen a lot of ideas from in terms of it does create Conda environments. That was run in Python or C++. We built in Rust to be sure that we can be as close to the machine as possible so that we can make cross-platform tools and that we're not limited just by the idea of running a runtime to run the tool in. That's also why Pixie has become a single binary. So the curl script you might have just run is not doing something complex. It's just downloading one file and putting it in the right place. Nothing more than that. And that's why I think that single binaries is the way to go for the installation of a package manager. You shouldn't need a package manager to install a package manager. Then virtualization. Pixie is built on top of the idea of virtual environments. So if you're not familiar with that, that means that you have a folder on your machine that contains the complete setup of that environment that you want to run. And these things are activated and deactivated or spawn up whenever you need them. So if you have multiple virtual environments on your machine and you activate one of them, it will not create a problem for another project that you're running. And because of this virtualization, we can actually easily split up multiple environments on your machine and make sure that nothing breaks while you're working on one project to the other project. Then cross-platform is a huge part of what Pixie tries to solve, because with the Conda ecosystem, we can get packages for all the platforms. So you just install the installation instructions for both Windows, Mac, and Linux. And there's just a little amount of tools that can actually do that. So if you use Pixie, you don't really have your readmes list different things on how to install. Pixie has different ways of installing on the different systems. And from that point on, everything should be the same. And then nothing to be shy of, Pixie is cross-language. This is definitely a Python conference, but going out of our way to also support all the other languages is something that we really value. So if you want to do C++ development, if you want to do Fortran development or whatever, Pixie is a tool you can use to streamline all of this development and don't need to learn new tools for every language that you want to use. So I already mentioned virtual environments. That is part of the three main topics that Pixie solves, which are, sorry, I don't want this here, and I think I will make this bigger. Yeah. So the three main things are the environment management. So Pixie will manage your environment. You don't have to think about that yourself. It's all done through Pixie. The package management, the solving, the installing, the updating of that is all done through Pixie. And we have task management. And task management means that the packages can be cross-platform or the project can be cross-platform, but then you have to run something. And if you use PowerShell, if you use Bash, if you use CSH, that might differ. And your project might be cross-platform, but what you have to run is not. So Pixie also includes its own task runner, so that you can create different tasks that run on all machines every time. And that's all built into the binary itself, which allows you to create simple commands for everyone to use. For instance, we often say, if you have something to run or serve or whatever, just make Pixie run start a task, and everyone can just git clone your environment or git clone your project and run the task itself. Then Pixie is built around the project workflow, which means that tools like Poetry, UV, NPM, and Cargo are big examples of project workflows where you have a manifest that describes how your environment is going to look or how your environments are going to look. And that file is then committed to a Git workflow or something like that, so that it is reproducible from not a command, but a file that contains all the information. And then the data of the environment is also close to that file. So if you're used to Conda environments or used to pip, you often install everything globally in your system or some location on your machine, but Pixie will keep the environment close to your folder. So if you're done with your project or you don't care about it anymore, you can just remove the folder and your whole project will be gone from your machine, making it really easy to manage these things where you don't have to have a global setup and a mental model of everything that you need to host. It's all done through like just the folder structure of your machine. So to compare that a little bit with some workflows that you might have been used to already and some pros and cons. If you use a system-based workflow, so you use opt, pip directly, or any of the other globally installed tools, you might experience a very simple installation, and it might also be already installed on the machine before you start using it, but you have a very high risk of conflicting things. So if you use opt and pip together, you might definitely get into a situation where tools are not working together, and that's because they're never built to work together. And this also introduces extra problems if you start building tools on top of that, like brew or pip together, where these builds are never built to run the same code at the same time. There's also limited flexibility and reproducibility because every OS has its own version of everything. So if you use opt on Ubuntu 20 and on Ubuntu 24, you might get a different package which is working on that machine, but you're not really reproducing the same environment you had before. Then we have environment-based workflows. If you're using Conda or Mamba or pip with a virtual environment, this is what you will be able to get. So it's easy to share these environments across projects. You will have an environment that you can activate. You have an environment that you can put somewhere on your machine. But you still need to keep that mental model of that environment. So you have to use the tools to figure out which environments do I have on my system, which environment has which dependencies on that environment. And then you have to deal with all these ideas around that. What you do get is the isolation. So you cannot really break in one project with another project if you just split them into environments, which is something we think is really cool. But to add to that, we created that project-based workflow for the Conda package ecosystem, where you can have isolated environments which are easy to reproduce because they're declarative, and then keeping all the dependencies close to your project. So you have a folder which is containing your full project, and it contains a manifest file to tell the machine what to install, and it can contain a log file to exactly log down which versions of packages you want, and the virtual environment will be in that same folder. So one project is one folder, and it should be a lot easier to manage. There's a few cons that some people notice, because when you share multiple folders, you might create like a lot of environments at some point, and that might introduce some extra disk space use, and managing environments over multiple projects is a little bit harder, because some of the data scientists like to use one version of Python with their matplotlib and then share it across projects. You have to kind of think the other way around, where the project manages the environment instead of the other way around. Just some notes that you need to take into account. Then, okay, so you might now know what Pixie is, but let's see if we can create a Pixie project, which is as simple as running Pixie init. Pixie init will create a little folder structure with the manifest file, which is called a Pixie toml. Or I added an example where you could say, okay, the format that I want to use is not Pixie, but is PyProject, because we also support the PyProject toml, which can just include some extra information to say, okay, for Pixie, you need to do this. And this is what all our manifests look like. For this tutorial, I will use the Pixie toml because it's a simpler format, and I'll continue like that. We also add some Git extra files to help you. You don't need these, but it's just there to help you get started. So this is a toml file that you will get. It will probably add some information of the others from your Git history. We'll add a channel. If you're not familiar with Conda, channels are... Oh, sorry.
Question. If I use pixi.toml
Yeah.
now,
Yeah.
later after we do this, I want to export it as pyproject.com, that's not a problem, right?
We don't have a command to automatically do that, but all the whole structure is exactly the same. So you have workspace, you have tasks, you have dependencies. You just need to add tool.pixi to it. And then you have the exact same experience. There's a few caveats that, because it's a very good question, a few caveats. So we also read the requires Python in a PyProject.toml. So you don't need the Python dependency anymore. It will read it from that. And you have the dependencies that are not in this example, but sometimes you, oh wait, it's here. This dependencies will be read as PyPI dependencies in Pixie as well. So yeah, it will just add a little bit of extra information to the Pixie toml. But yeah, it should work out of the box. This was actually great. So if you have questions, feel free to ask them. So next is, how do I manage dependencies? So like every other package manager, there's just a command for it. You can use pixi add to add a dependency to your project. This is exactly the same as uv add or pip install or conda install, but it will add it to the project. That's why it's called add. You can give it normal dependency names, but you can also give it more specific names. What it will do, it will add it into the dependencies of your project, because the default one will install the conda dependencies and will give you the dependencies in your list. We pin it to the last installed version, but then using semver to pin it to the major version of that. In a log file, we'll create the actual exact version that was installed. This is something you can configure if you don't like this form of pinning in your manifest file. Yeah, so what I said, you can also just define specific versions you want to add to your projects. There's more data on this, which I won't talk you over, but a lot more you can do. A quick example of what you could do is like adding a channel for a specific dependency that you have. So I want this package to come from Rapids, then give it the Rapids channel instead of the CondaForge channel. but there's a lot more configuration that you can do. And as said before, Pixie is not only a Conda package manager, but it's also a PyPI package manager through its PyPI dependencies. So a lot of the CLI tools have this extra flag called PyPI, and if you then add a dependency through it or do some other configuration, it will act on the PyPI side of these dependencies, and it will install them as PyPI dependencies. And Pixie has some extra smart logic in itself where it uses UV and the Pixie Conda solver together to figure out, okay, I'm going to get these dependencies from Conda, and then it will tell you, hey, you don't need to get these dependencies anymore. For instance, if I have the NumPy Conda from Conda Forge, I don't have to get it from PyPI anymore, so you don't get clobbered environments where you get runtime issues because two of the same dependencies were installed by two different types of systems. So we use the PyPI setup as an additive to the Conda environment instead of breaking your environment, basically. And it will look like this. So if you add a normal dependency, which is in Pixie world a Conda dependency, it will go into the normal dependency list, and everything PyPI will go into the PyPI dependencies. And yeah, just that extra notion, like if you added Pydantic as a Conda dependency already, you can still define this, it's not a problem, but it will not reinstall it as a PyPI dependency. It will see, I already have this, I don't have to care about it anymore. And as mentioned, for PyProject, it will not add it to the PyPI dependencies, but it will add it to the dependencies of the project, which is in PyProject world the normal way to do this. One more thing to add to that, because if you install something with pip, you're very used to doing pip install dot and then editable, for instance. In Pixie, because we have this declarative manifest, you have to define it in the manifest itself. You cannot, on the go, add something to your environment while it's not being defined in your manifest. So something like this will be added in your manifest to say like, oh, next to all of these dependencies, also add my local dependency through these path dependencies with an editable flag, yes or no. A little mention that you really should know is we use UV internally to solve all these PyPI dependencies, but we're not installing UV for you. Not like how Conda did always install pip for you. We use UV in the Rust code because it's also a Rust project. We can just link to that, and it will internally use that. So don't expect UV commands if you have Pixie installed. Yeah, some extra cool types of dependencies that you can have, for instance, Git or paths or URLs, all work. Then the log file itself. The log file is always called pixie.log. A lot of the languages or package managers have a similar file. The log file is always automatically updated if you add something, subtract something from your environment. So all these CLI commands will modify the manifest to add the dependency that you have, and then at solve time, it will also record everything that is present during the solve in your log file. And if you share this log file with others, it will not just create a similar environment to what you have, but the exact same environment as you had, making this reproducibility problem a lot better to manage. And the file itself will be a human-readable YAML file. It's not meant to be edited by humans, but at least you can read it to figure out what is my environment actually containing during the run. Just a note, not only add, remove, or update will write these log files. If you already have a manifest file that you have modified yourself, Pixie install will find out, oh, I don't have an updated log file, let me update that for you. And it will recreate it. This is how these log files look. So just so you know, it's not something that you have to know to understand Pixie, but at least it's like a human readable format, and it will lock it down to like SHA hash level of which package to get instead of just the name of the package with the version. Then going on, Pixie is not just a package manager, but also a task runner. So you can add tasks to your project, which allows you to easily run cross-platform commands. For instance, echo is something that's not supported directly in a similar way as on for instance, Unix and Windows, but using Pixie, this will all run exactly the same. So if you do a Pixie task add hello, and then what that task would be, then in your Pixie toml, we would add this alias. So it will say hello equals that. And if you then run Pixie run hello, you will run this exact command, and this is something you can easily share. So this is an exceptionally easy example, but you can imagine if you have some complex setups that you need to do or some prerequisites for running your system, putting it into a Pixie task, allowing your coworkers to run a single command makes it much easier to share your work with everyone. There's actually more on this, but I don't want to make this too complicated for now. And then after having these installed environments, after having these tasks that you can run, Pixie never runs this on your machine directly. It first has to activate these environments. This is the idea of virtual environments. So Pixie run or Pixie shell will start up the activation of that environment and will put you into that environment directly. If you use Pixie run, you can run any command that you want. It will be run in that task shell that was just talking about, but you can just directly say like Python v or the whole command that you want to define. If you want to run a task, the first name in your after Pixie run is the task name that you're going to run. All the trailing arguments will be pushed towards the task itself. And otherwise, Pixie shell is equivalent to sourcing your virtual environment or CUDA activate or something like that. It's equivalent to that. So you just start a new shell, and in that, the activation of the environment has happened. I'll skip that one. And next to being able to add one environment to your project, you can actually have multiple environments. So that's something that looks like this. Let me check how the time is going. Still good? Great. So we have a concept of features and environments in the Pixie world. Everything that you just saw was like dependencies and tasks in your TOML file. Those are always like virtually prefixed with feature.default and then dependencies, because that was all the default feature setup that you were doing. If you want to like do more with your environments, you can actually add more features. So you have to think about this as building blocks for building an environment. For instance, a feature could be the test feature, where you want PyTest, where you want other testing tools in your environment, but you don't need that in all environments. For instance, if you're shipping code to the cloud, you might not need to run PyTest in the cloud. You might only want to run that in your CI. So if you strip that into its own feature, you can then define different types of environments. So here I have an example of the default environment, the test environment, production environment, and a format environment. All of these environments have related features. So the test feature, the format feature, and the debug feature. And as I told you, the default feature. What you can see is that the default feature has Python and NumPy, but when I want to test, I want to add PyTest. When I want to format, I want to add rough. And when I want to debug, I want to add IPython. And mixing these features together into an environment allows you to have different types of environments that look very similar or not, depending on what you want. And then there's one extra thing that I want to mention is the solve groups. So as you can see, default, test, and prod all have the solve group default, meaning if I solve this, all of these environments are seen as one, and I will solve all the different packages to the exact same version that I want for all my environments. But then as I'm running them, I want them to be stripped away. So my prod environment only has the default features, but the default feature, so only Python and NumPy. But my Python and NumPy will be exactly the same version as the version of Python and NumPy in my test environment. And this is very important when you want to make sure that what you're testing is actually also what you will be able to run on your production environment. This makes it very easy to slim down your Docker images for production, but not have the overhead of making sure that everything is on the same version. Pixie will do that for you. And then if you want like a super minimal environment that is just using rough in this case for formatting, it doesn't need Python, it doesn't need anything else, you can say like, don't use the default feature. I'm not going to need that. And then the environment can be much smaller and doesn't need any of the other features. It doesn't have to be solved in that other solve group. Just spawn it for me if I need to do some formatting. So in this little example, I have a diagram that shows it. So the different features that you define all are pointed towards different environments, and these environments are then solved together as one solve group, resulting in no conflicts between these versions and making sure that what you're testing is what you're running in terms of the versions. That was actually the introduction to Pixie. The next step is exercises. Is there any questions before we go there?
Maybe I was just looking, so when you solve the environment, it
Yep.
basically tops up all the different sub-dependency versions, solves it the full lot, hashes them, then it just picks out the hashes.
Yeah.
Through, so
Yeah, it does the splitting automatically then after that. Yeah. Yeah. Yes? Mm-hmm. But like the only requirement for a PyProject file is that you have a name for the project, and I believe that's it. So that's the only overhead that you have. Like the rest is just dependencies.
Name and version either has to be specified or set as anything.
Oh, yeah. Yeah, so it's like there's a minimal amount of effort to make that file itself. Like the interesting stuff happens in like, okay, what is the configuration for this environment? And where I'm not sure how you do it right now, but you might have a command to do like install this or this requirements file or something like that. Don't use that, just use the PyProject.toml or the pixi.toml and you will get complete project experience while not having and also having the reproducibility from that.
Remember that the PyProject tunnel is an option. You can just have the pixi.toml without all the Python package stuff. So it's totally fine if your workflow is a repository. If you don't have a Python project inside of it, then you can just, there's no need to use PyProject.toml. You can just use pixi.toml.
Does that answer the question? Okay. No, it's just a different format. There was one before you.
If you have a CUDA environment and a pixi environment in the same shell, what makes precedence and do they split?
Yes. What happens, like any CUDA environment or virtual environment for that sense, it depends on which is the first in your path. So CUDA activate or pixi shell will all add it to the path variable in your shell. And then when things are run, the logic of the shell will look into the path and will pick the first folder that has the executable that you're running. So if the Pixie's environment is the first in line and it has Python and you run Python in your shell, it will pick Pixie's Python, and because the Python interpreter has that path, it will work for all the Python tools that you're using in that environment. If you then expect it to pick up stuff from the CUDA environment, there might be problems with that, but that just depends on how you set it up. It's not advised to use them together because you might create these problems for yourself. But yeah, it's all just shell logic that's happening there.
I don't think that we covered this, but also if you already have Conda environments, you can import Conda environments into Pixie workspaces. So there's a migration path.
Yep, definitely. One in the back. So to rephrase, you want one global environment and then just install editable packages into it? Yeah, so one thing to note is that Pixie is heavily caching everything. So while you might start creating lots of environments, that doesn't mean that you're copying code. So when an environment is spawned up, it will download into a cache, and from that cache, it's symlinked into or hard-linked into your work folder, and that data is not per se copied. So you don't really have to worry about disk size on that level of the experience. And the benefit is that you might like at some point be like, oh, I just want to pull off and do a little bit extra in this project and do a little bit extra in that project, and not have to think, oh, but my other project is also using the same global environment, which I don't want to break. That's basically the idea that we're solving. While you can still do it, like it's still all possible. You can make in theory, one global project that you can add everything to, but I wouldn't advise that workflow as a developer for Pixie. I'm gonna go first to that one.
My team's entire workflow today is containerized. So we have bespoke Docker containers that we have Python and R pre-installed with all the packages.
Yep.
We split it up and use these. And today we use UV for the Python side.
Yep.
But for R, we just use RN and other bespoke code. Can I integrate Pixie with this workflow? How do I? Or are you going to come up with something?
This specific topic we're not going to cover, but yes, you can completely replace the workflow with Pixie. In like 99% of the cases, we cover the same amount of stuff that UV does through UV. Like if anyone is from that team, they did an exceptional job at supporting that part. Pixie just adds a little bit of layer of mixing different dependencies, like the art projects, like the extra compiled projects that you need, with the PyPI stuff. So if there's something not available in Conda, then you can still use the PyPI ecosystem to solve that part. So yes, definitely. And also R. R is also supported through CondaForge. Oh man, this is hard. I think you already had your hand up for a very long time. Yeah.
I wanted to piggyback on what 2 questions ago. So,
Oh, okay.
concrete example, suppose I frequently work on 2 or 3 projects and their interactions. So I want editable installs.
Yeah.
Or maybe I'm a maintainer of a major project and somebody has a report about unmerged branches of projects. Do you create a sort of thin project directory to define those editable installs? Or what workflow would you recommend?
So if you already have a setup project somewhere and you want to use an extra project or library from source, you can just change that dependency. I might not get your question completely.
I guess it's hard to know where that should live because I don't want to modify the pyproject.com of any 1 or 2 or 3 projects. I want to have a working space which is all very active in Conda, some environment that defines some.
So Dan, let me see if I get your question right. So you're saying that you are working on your cluster or whatever, and you have 3 separate Python projects that all live in different directories.
Right.
But you want an environment that has them active, but you also want all of them to be editably installed, correct?
Yes.
So if you, so I believe so Ruben can give like the definitive answer here, but one thing you could do is if you're just using like a pixi.toml, when you're defining your PyPI dependencies table, if you want it to be editable, you say editable, but you give it a path.
Right.
So that path is not restricted to just the directories below you. That can be anywhere on any machine that you can get access to. So if you know, unless you're going to be moving your Python projects around willy-nilly, and if you know that path, then just put it there. And hopefully all of this, if all these tools live together and are actually edibly installed, maybe there's some bigger global meta projects in which they are already going to have defined relative paths to each other. And then you just put it in and you're done.
Yeah.
Yeah, that makes sense.
And if you want to go even more hacky, it's just a Conda environment. So just pip install it into your activated shell. That works as well. But that's 0 reproducibility guarantees. Sorry?
I've got it, but I wasn't sure if that was the cleanest way.
Yeah, great. You have your hand up. Great.
I have a little bit trouble understanding this project-based workflow thing. For me, it's such a good idea to couple the environment to this project. In PyProject, how you typically use to define something that will eventually be a Python package. Then you can install multiple Python packages into one environment.
Yeah, so the notion of a PyProject toml being used for building the package is like, it's definitely useful for that, but it's not mandatory in any way. It's like just a configuration file to define the dependencies of your project. If you would then want to build it at the build system like this, like we automatically add that for your convenience because editable installations might require it. But it, like, some people still use setup.py, I believe, which is like the old version of this, where you would define a script that does the installation. And this is all being standardized. Like, I believe PyProject toml started 10 years ago. And I think this is now the most advised way of dealing with just installing a Python environment. It doesn't have to be a buildable project in that matter.
Can it actually have tools that can have like definition that tells me how to set up an environment?
Yep.
And they can also have like configuration of the package.
Exactly. Yeah, yeah. It's like Pixie has the same feature where you could build a conda package from a Pixie environment if you want that. Yes. Sorry.
You said that Pixie does a good job of keeping your dependencies from conflicting.
Yeah.
I frequently run into a problem where I have several packages from R that are no longer supported on R. Would it be possible to create a Pixie project where it's just all these older legacy versions of R with various packages and just have that be a one-stop shopping where when I need to go through these legacy programs, I just pipe into my Pixie?
Yes. So I showed you the example of using different environments to have multiple levels of environments. But a great feature is, or a great example of this is also, I think in a Python version of that, that would be multiple different versions of Python. So have 10 different environments for 10 different versions of Python. And then if you want a certain version of Python, you just activate that one. Just Pixie shell into that environment, and then you have that version of Python. The same thing can be done with R. So if I have an environment that works with this library from R and this version of R, make it into a separate environment, give it a name, and you can just do Pixie shell into that simple environment. Yeah. Exactly. And then because it creates a log file, you can just add it to Git. And then if you completely remove your machine, you reinstall it and it will be there in seconds.
So I think for time we should probably move on to the exercises, but it's clear there's lots of great questions.
Yeah.
That doesn't mean don't ask them, but we'll come back to them.
Put your hand up and we can definitely talk more. To get you started on the Pixie exercises, the idea is for the exercises, you start them on your own machine. If you're limited in any way on your own machine, you can use the Brev instance to run these examples. If you need help with that, put up your hand, and otherwise we can help you. Every exercise has just a few things that like trigger you to think about, okay, how can I do this with Pixie? If you're like completely stuck, you can look at the solutions. In theory, all of the solutions should already be mentioned in the document I just talked you over. And otherwise, if it's still stuck, then just call us up and we can help you with the exercises. But this should at least give you a good introduction to all the main features of Pixie. That's the introductory exercises. This is for you to figure out. Then, good luck with that. We'll be walking around for more questions.
Also, you don't have to quietly work on them.
Yeah.
Collaboration and discussion is encouraged.
Yeah. And if like the plan was to take like 45 minutes for this, I believe. Let me check. 40 minutes for this. Just let us know when you're like done and want to continue. Maybe we can already talk to you with the extra projects. And if you need extra time after this, we'll still be able to help you continue with the work, but you don't need to have this done to continue with the extra exercises. So don't worry about that. And after this, let's get a little break to like get all this information to settle in the brains.
40 minutes should be hopefully a very generous period of time, but if everyone is done early, and make some noise so we can get to
Yeah. Got the codes to work again?
Not yet. They're making new codes.
We're done.
Sorry.
It was empty?
Yeah, we have so many people that signed up that we used all the codes. So that's good.
That's great. Yeah. That's a great code.
Yeah, I know, right? So.
How's it going? Everyone moving forward? Yeah, a little bit too quiet. Was it too easy or was it too hard?
Yes, do I?
Yeah, so basically,
people that did not get the code working before to get Brev working, we have gotten another 50 codes from NVIDIA. So I'm going to put that in the chat. Okay, so okay, so the new code, if you didn't get it working before, is nv-scipy-summer-25. So the same thing, but just with nv- prefix in it. And it's now also in the chat. Okay. So if, I know that people are working on the exercises, but if you didn't get things working before, please try this now. So go to the NVIDIA billing, the NVIDIA Brev billing page and put in NV SciPy Summer 25 and make some noise if things don't work. And while there's instructions in the setup, if you don't remember how to get there, if you do just brev login at the command line, that will then prompt you to get logged back into the system. Sorry, it's 2025, not 25. I can't read.
Make that like one time.
And then I'm also going to edit the Slack message.
Oh,
I got excited. Okay.
Is anybody still having issues with the code?
No, it wasn't.
Raise your hand if you're still having issues with the code. No one? Everybody got the code to work. I fixed another one, but yeah, I want to make sure there's no more. Good? Do you?
queuing the concourse channels. Yeah, if it isn't available for your platform, then it won't be able to install. It's only available for something. Yeah, it's not concourse, but it's only available for limited access and available for OS 10.4. Oh, but it's not available for Apple, for AIS, for OS 10. So maybe that's why. This is the that this specific requirement, and it won't install P8. What it just says failed to solve. It says the same message as first does, or does it get
Anyone else still having Brev issues? No? All good? Sorry. Does anyone have Brev issues still? Just raise your hand if so. No? Any other issues?
we install mini forces, and then just trace, just whatever you do, don't have to trace environment. You can have one other environment and use that for everything, but just don't touch the base environment. And if you ever delete the environment, just delete the environment because we create don't reinstall the whole thing. So even if you just use one environment, just make it not a base environment. In hindsight, they probably should have made a base environment because you just had every environment be like, there could be one default environment, but it's like it's not special, so you can delete it. But the way you get it, there's itself kind of the base environment. It's kind of forever. Well, first of all, I thought that John, he said that local he installed it or something. Pixie is also.
I think the PyTorch example is frozen because of something like on the PyTorch example is working for people. We have two issues. One with the package that's it's maybe a generic almost a package that's only on the board, and then also we try to package it only in PyTI, and it also can. But I'm not sure if it's just it's not clear why it's not doing it because of the constraints there.
Yeah, so it will not start automatically searching on the object. If this assumes you are adding it from the button, then you can add it back to the white where they're searching.
So if you actually find that, will it still? There's no way to just. Yeah, there's no way to just automatically pick it up.
Here we could, but it's all white is so insanely large. One thing you or so it's like one problem is so so Pixie is not just white mark because one more. Yeah.
Hey guys, we just heard that the PyTest example or PyTest workflow doesn't work from Git. This seems to be a problem that the main branch of PyTest isn't working properly anymore. That's a fault on my part because you should never depend on main for something like this. You can try it if you feel the need for it to use the latest tag like the extra example is doing, but otherwise just skip that example. It's not necessary. It's just showing you that you could use Git dependencies, which might be beneficial if you're developing something yourself. But it's not per se recommended to use a main branch from an open source project. And next to that, it's also around time to do a little break. So feel free to get something to drink and come back later. If you have more questions, we will still be here. Sorry?
come back in 15 minutes.
Yeah, so there will be 15 minutes. So if you're back at 15:25, that's all fine. And we're going to restart. Or stay here and we can still answer questions, but know that you need to let this information set.
Thank you for also pushing things to
Yes.
credits for everyone.
Yeah, yeah. Well, I'm glad you responded. I was like starting to write an email. It was like,
Yeah.
and then once you got it, like I was about to say,
it's
okay, I
like-
started asking questions, and then you were like, came up there, you're like, oh, it's done. I'm like, perfect. No need to do this.
Yeah.
Yeah, but if you don't do anything, if that I would solve it.
All right. So when we come back from break, we're going to be using Brev. So please make sure if you haven't gotten Brev set up yet that you have logged into it. So we're going to basically, for the rest of the tutorial, we're going to be using Brev. So everything that we do now will be in a shell environment on there.
Also, if you haven't seen, we have some stickers up here. Feel free to help yourselves to those.
After how many years in Python? Here's the thing, these two fighters don't mix these and on that. It's all about the simultaneous. Yes, yeah, we do.
I'll do that. Okay. So I basically thought more about correctly starting off from a project and then initializing it, add icons, or add all workspaces. Yeah, sure. They're going for all of them. Add pandas after the stuff through Python. That is like especially for those that don't like the list for the last. You get down to adding pandas. There's automatic on the board, I guess. It fails because asking for I think that for even though you're now in this one three. And if that is a function by NVC and I like that and then Pixie and there's that is fine because no, yeah, I mean, well, yeah, you actually have it in the directions that it's optional, and I think it might be, since I wrote this a week ago, it's not optional. You know, and now, okay, yeah, so, that's okay, it's just one thing. Yeah. probably because they're already added it with IPI. I would assume. You try and install a transport package on top of them, I guess. Recipe for disaster. Too much stuff. Like in theory, you could uninstall them, reinstall them. Probably would work, but you would have to like install them. In such cases, like those. Well, but it's installed on it, and it's like, I'd have to dig it up. Like you install it in a fresh environment, like you create an environment just for it. I'll use like, you know, oh yeah, but it was, I don't know, it was delayed by like 3 hours. And so it only got to here at 3:30, and I don't get to the hotel like 4:30. And that was 6:30 my time, so it was like, you know, it was, no, the first one was delayed by an hour, but I was having stuff connected. The second like I was like 3 hours. At least, and before the meeting, they haven't even close to an example. They got an example out of it. Dallas. It wasn't like, unfortunately,
I'll just like take this off just to be like clear.
Sure. The one thing I'll do beforehand is just make sure that
Everybody's got it.
Yeah.
Perfect.
Okay, we are back from break. So hopefully you might have gotten up and gotten some water or coffee. So everyone, I believe, is at a point where, so we've done some exploration of Pixie. For the rest of this, we're going to be using like clear packages from either PyPI or Conda Forge. And so kind of the installation setup should be more clear. We're now going to be doing basically the rest of this tutorial on Brev. So everyone should have already started up their instance. And what we're now going to do is I'll log into Brev together. So as was mentioned, to connect to the instance, you can do brev shell and then the name. So in this case, it's Pixie CUDA, and that's going to SSH you there. So we're going to do that together, brev shell Pixie CUDA, and hit enter. And so, okay, so we've now SSH'd in, and so if I now do pwd, I now see I'm under home Ubuntu. If I do cat, etc., OS release, I now see I'm on a machine with Ubuntu 22.04. And if I do NVIDIA-SMI, oops, that was very large. But you can see the important bit there is that there's an NVIDIA L4 GPU. So to make sure that we basically landed on a almost totally blank NVIDIA machine. And so to make sure that we're all on the same page, we're going to go back to the setup instructions. And if we go down to the very bottom, then now that we've all landed on Brev together, we're just going to very quickly install Pixie and make sure that we also have our Git tools. So we're going to first, I think that was, I'm not sure if we're going to basically just copy and paste these individual lines. Everything is nice and snappy because we're running on a machine with good internet. And so all we did is we installed Pixie. We also went ahead and made sure we had its shell completions. We're now going to source our bash RC to make sure that we have Pixie back. If we do Pixie version, we see we have Pixie installed. And then we're also going to do, Pixie global install GH for GitHub, and it's doing a solve real quick, and we have GitHub installed. So everyone should be at this point, and we're now going to turn it over to John to introduce us to CUDA and CUDA packages.
Thank you, Matthew. So everybody has Brev set up, SSH'd in, Pixie installed. Anybody struggling? Okay, thank you. All right, I'm going to try to give a relatively quick overview here. So CUDA is a programming language developed at NVIDIA to work with GPUs. It's designed to work on highly parallelizable code. So if you think about working with arrays, for example, like adding two arrays together, like we do in NumPy pretty regularly here, or if you think of doing matrix operations, like matrix multiply, computing norms, this kind of thing, this is the kind of thing that CUDA is very well designed for. And it works well with other languages. So historically, C and C++ have been the best supported, also Fortran. But increasingly, Python is a focus, as well as other languages like Julia and Rust. Of course, in this context, we're very interested in Python and Python integration. And then, of course, CUDA is like a closed source language. So to make it easier for users to get CUDA packages, historically the way to do this was you ran a CLI that installed everything on your system in one location, and then you maybe install system packages somewhere else, and you try to get those to play as nicely together as possible without anything breaking. Anybody had experiences with that not going smoothly? Yeah, I hear chuckles, I see people raising hands. So yeah, so this was historically hard for users to set up. So to try to make it easier for users, we tried to add Conda packages so that users could install all of the CUDA toolkit. We started initially just with runtime libraries, so focused on things like cuBLAS for doing math operations, cuSolver for doing like LAPACK kind of things, cuFFT for FFTs, so these kinds of libraries. And initially we put this in a giant bundle package which you can see has like this one name of CUDA toolkit all together. And we started building things in Conda Forge so that they supported this package. And we did it using a Docker image that also had all of the NVIDIA compilation tools in it to set up this build. This worked to add initial packages and roll out for a bit, but then we learned a few things from this process. In particular, what we learned is this package is kind of big. So users would sometimes complain about getting too much stuff installed at once if they just want one little thing, or if they're just using the CUDA driver or CUDA runtime library. And then in other cases, it didn't have everything that they wanted. Maybe they wanted some pieces of the compiler toolchain. Maybe they wanted some other libraries from CUDA that weren't in that redistributable package. So it was kind of too much and not enough at the same time, if that makes any sense. So to try to improve this, we added the revised set of packages. I'm not going to go into too much detail here, but the main point is we tried to match how we did packaging in other system package managers. So has anybody ever here tried to use like apt-get to install CUDA packages or yum? Maybe one or two. Okay, so you kind of have some familiarity, maybe a little bit of what that would look like. So we tried to make the Conda packages look like that. So if you're coming from that environment, it would look similar. The names would be similar, and you get similar behavior from the packages when installed. When we initially did this, we rolled this out on its own channel because it was a total restructuring of the packages, and in many ways a breaking change from what we had done in the redistributable package. So we wanted to try that out and see how it went. And then after that, in 2023, we started adding this to Conda Forge with feedback from the community. We did this in particular starting with CUDA 12.0. So any versions before CUDA 12.0, they use the old style packages in Conda Forge. Anything 12.0 or later uses the new style packages in Conda Forge. Does that make sense? Any questions about that? Also, feel free to just interrupt me at any time and ask questions. So we added these updated packages. These include everything, not just the set of CUDA libraries in the redistributable set, but libraries beyond it, also developer tools. So you have compilers, you have CUDA GDB, you have NVProf, you have like every tool in the tool set that you would get from CUDA Toolkit except the driver. The driver is the one thing that you would still install at the system level, but all of the packages then live in Conda. If you wanted the equivalent of just installing the entire CUDA Toolkit, there's a meta package called CUDA, and you just install that package with whatever version you want. So say I wanted 12.9, which is the latest version of CUDA 12 available. I could just pick CUDA 12.9, and that would install everything. And I can do this with Pixi. To make it a little easier to understand what your hardware supports, because some features in these libraries depend on particular hardware features and on particular pieces of the driver library, there is this CUDA __ meta package. This tells you about what your driver's capable of running. So if you look at like Pixi info, this will tell you what that version is, and then you just don't use any versions newer than that. And actually Pixi will constrain based on this underscored CUDA package to make sure nothing newer than that gets picked up. So this provides a little example of what you might see when running Pixi info. So imagine I'm on a Linux 64 machine, so this could be very similar to the machines that you're on now on Brev. This will tell me my Pixi version. This will tell me that it's Linux and it's x86 64. That's what that's telling me as opposed to ARM. It's also telling me that it's a kind of Unix. It is a particular Linux version. There's a glibc version associated. And there's a particular CUDA version that's supported. It can also tell me things like what kind of CPU I have, if there's like a microarchitecture that's specific and important. as well as other general config information. Okay, so how would we actually use CUDA with Pixie? As you can see here, we can just add in system requirements to specify what CUDA version we want. So if I just don't care and I just want 12, I can just specify 12 and I'll get the latest version of 12 that I have available. And for most people, this is probably fine. And then I can do this in the existing environment that we already have. So you could create an environment here. Oops. Yes, I'm still using Mac commands on a non-Mac machine. Oops. Where were we? Yes. Yeah. I didn't copy it right though. No, apparently not. Okay, let's try again. Nope. Oh, shift. Yes, okay, that is why. Fair enough. Okay, so I've just copied the same command that was here. I say pixi init, and then I say cd, and now I'm in this directory. So let's take a look. What do we actually have? So here's my pixi toml file. You can see this is the workspace. It's using the CondaForge channel. The name is just CUDA example. We could change this to something else if we wanted to. Currently, platforms is just Linux 64. If we were trying to do something for Windows, we could change this. And then just kind of a default version here. Okay. Is everybody able to do that so far? Good? Questions? Okay. So now if I want to go ahead and add CUDA 12, shift. Okay, good. So we can see now it has CUDA 12 there in system requirements. Yeah, and this is just showing us the same thing. Okay, so I could then take this environment and say, actually, I want CUDA 12.9, oops, specifically. And see, now this has added it into dependencies. So we can also actually look at the environment itself. Oh, okay. Okay. Yeah, so you could run this as well locally. I'm going to skip this here, but this will just show you all the information in that environment. This shows that it's going to be CUDA 12.9 and the packages that are installed there. So, okay, in terms of hardware support, you can't, Mac is not supported. So you could do Linux, you could do Windows, you could do Linux ARM. Windows ARM is being worked on currently. So those are the target architectures that you can support. Yeah, and so then this is specifying how we could add Pixie workspace that's multi-platform. I think in our case, we would just add Windows. Yeah, so if I want to do this, I would do yeah, and so now you can see originally it was Linux 64, like if I scroll back up, right? Now we also have Windows. And I could do the same thing where I add like, let's say I want Linux ARM. Huh? Oh, Linux, sorry. Yeah, so we can see Linux 64, Win64, Linux ARM 64. Does that make sense? Questions? Okay. Yeah, and then we can list specifically what packages we now have installed. Oops. My muscle memory is not helping me here. So that currently we've only installed CUDA version, so that's 12.9. We could go further. We could say, let's go ahead and add all of CUDA. See how long this takes. Pretty far along already.
This is more fun on Brev than it is on Maven, because the speed here is not similar to the Brev instance.
Yeah. Yeah, this is pulling in the kitchen sink, literally. Yeah, so I can now do things like which NVCC, which I couldn't. Oh, I need to. Yep, so you can see MVCC is installed in that environment. I could do something like, what version of MVCC are you? It is indeed 12.9 as expected. So yeah, I have fully functioning CUDA toolkit available to me now. Easy peasy. So this matches pretty similarly to what we would have gotten here. All right, let's add something a little bit more interesting. Let's try adding PyTorch here. I mean, I already threw the entire CUDA toolkit at it. What's like PyTorch? Uh-huh. Almost done. Has everybody gotten to this stage? Any issues? It's too smooth. I'm like worried you're, oh, one? Okay. Oh, okay. So we're about to hit issues. You've just gotten very far ahead. Okay, good. I get worried if there are no issues. All right, so let's do a Pixie list, see what's here. Ah. Beautiful. So we have PyTorch here, CUDA 12.9 build. If I did Pixie run Python, torch. There it is. Oops. Do not log out of it. Yes. Too emphatic. Yeah. So now we have PyTorch. This is the same thing that we've got in here. So now we have a little example. Why don't you give this a try? We'll give you like, I don't know, how are we doing on time? A couple minutes? Yeah? Give you maybe 5 to 10 minutes on this little exercise and see how that goes. Question? No? Okay.
So this is the example. The exercise is 2 lines down, which is basically like you, in the previous example, you might have seen or might have not gotten to the multiple environment example. In this exercise, you're requested to not do exactly this, but create 2 different environments, one specific to CPU and one specific to GPU. If you have any questions, I can still re-explain that part because it was not, if you might have not reached that in the example or in the exercise, it might be a little hard. But you can create 2 different environments where you in one also add like OS X, so it will be runnable on OS X, and the other one will be for every CUDA machine that's out there. That's the idea. The solution is still there, so if you're stuck, you should be able to go through that. is everyone able to get to this GPU example? Or is there something that you still have questions about? Please just ring the bell.
Can I get a show of hands of how many people have gotten through the example at this point? It's like maybe half.
Well, that's why the spider, you can connect to this thing, the spider, and do everything with spider, just like you would do. And the output, there's still doing those for spider. This is a demo on Friday, how to do it, but it's still not, making, just putting all the features, could have been playing all that. Well, the stable version in progress. Yeah, so Spider would allow you to manage the file system, upload like sync and upload now with 6.2 to the edge file without even having to sync them to your machines. You know, you have all the full complete here, help and they can proxy my code, remote projects, remote environment. So, access remotely and yeah. That's definitely the case with file system abstraction. Yeah, with Spider we're actually implementing Pixie for the backend, environment packaging with Spider. And I guess that's because I'm mostly using that. Okay, then you don't have to worry much about creating the project out routine, but if you use the Spider project and all that activate the Pixie environment for it, and all that export that, things like that. And even on but the benefit is that if we do this in the remote machine, you don't have to do all this manual stuff. Spider actually.
All right. I think we're going to go through the solution real quick, and then after that we can take a break. And if you guys want to continue working on a break, we can do that, or you can take a break and we can move on to something else. Okay. So like before, we were saying you can extend the environment to different OSs. This will add it to the platforms list as before. But in this case, what we're wanting to do is we're wanting to separate out the CPU bits from the GPU bits. So in order to do that, you're going to have to use a feature to distinguish the two. And with the CPU feature, then you can use the CPU version of PyTorch that has no GPU components. and then add this. So now you'll see that this gets added underneath in this feature selection with a separate set of dependencies. So this is no longer under the general dependencies for all cases. This is only if the CPU is active. Oh, yeah.
Does everyone understand features versus environments? Because I've had questions on that before. You want an explainer on that? Yeah.
Okay, you want to, yeah.
So features are a way of defining an environment. And you can think of it as a building block that you can define. So a feature can contain dependencies. It can also take tasks, which you might have already seen. It can also take platforms like channels, can basically take the full definition of what goes into an environment or what you can run in an environment. But we named it a feature because you can have multiple different features in one environment. So in this example, you have the CPU environment, which you add the CPU feature to. But you can also add the test feature, like I had in my example, where you add PyTest. So the PyTest feature and the CPU feature could be added into one environment, for instance, CPU test, to benefit from both of these building blocks that we define. And this is designed like this because in most cases that we have seen, you're going further than just a CPU and a GPU environment, but you might have a Python 12 and a Python 13 and a Python 14 example of this. So you can kind of make a matrix of all these different environments that you want to be able to support, but building through these building blocks. So you don't have to redefine dependencies multiple times, avoiding like multiple different sources of truth of different dependencies. Does it explain it a little bit better?
Do you give an example of how
Yes. Because that was in my Pixie introduction. So, fortunately, it doesn't have formatting, but as you can see here, the default environment that we created here has the feature toolbox of test, debug, and format in one go. And as it's always supporting the default feature in this line as well, so it expects you to say, I'm using the default feature and these extra features. And that is just a combination of all these different features into one environment. So you have to think of, let me go to the mic. You have to think of it as I'm defining features, but I'm running environments. And an environment is a set of multiple features together. There's always the default feature, so you can disable that with no default features, like we've done for the format. But for the rest, if you want more, I just define a new block of features that I want to add, and yeah, build it up like that. Does that explain it for you? Yes. Yeah. So the solve groups were the part where if you have multiple environments built with multiple different kinds of features, you will put them into one solve group. So at solve time of the dependencies, it will see them as one environment, making sure that Python, that PyTest, that CUDA, if you have that, are all the same exact version in all these environments. And then when you run them, you run the specific environment, you only run a part of that, and you only have to install or download a part of the dependencies that link to that. Yes?
Could you have different features with conflicting dependencies if you have a feature environment that requires?
No. That's not possible. The problem here for the solve group is that it needs to be run as one environment at some point. What it will do, it will not like take one before the other. It will combine the dependencies. So if you have a dependency on Python 3, whatever, and a dependency in a different feature on Python 3.12, it will see like, okay, I need 3 and 3.12, and that works because 3.12 is also 3, so it solves. But if you have like one lower than 3.12 and one higher than 3.12, that will conflict and it will not work. If that explains it, then I would like to give the mic back to John.
Thank you. Yeah. So the idea here is we're using features to separate GPU and CPU cases and just kind of grouping those sets of dependencies separately. That's how we're using it here. So very simple example of how we might use them. And then you can similarly, yeah, this is just telling us the GPU bit. Any questions on this solution? Yep.
I think I can explain that. So what Pixie Add will do is if it can already like install that environment and it's a default environment, it will start doing that. So if you modified something that it expects you to also want to install, it will try to do that. But if you don't have the environment defined yet and only have Pixie Add of that feature, it doesn't have an environment yet to install, so it will not do that for you. It can also not lock because there's no environment to get the full picture. As soon as you have that environment available, it will be like, oh, I know which one this needs to be updated, so it will do that for you. But if you run anything, if you want to use these environments, it will also recheck, like, did he already install this? No, I will do it for you. So you don't have to worry about like, oh, it didn't do that, now I have a problem. As soon as you want to use that environment, it will do it for you.
So what Ruben said is correct, of course, but
Okay.
to answer Matt's actual question, you mentioned there's repeated commands, and that was because of a typo on our part.
Okay.
Pixie add should have been Pixie upgrade.
Oh,
So,
okay.
yeah.
So-
I mean, basically, there was a line there that somehow we missed that when reviewing, but that's my bad. So in that case, the Pixie upgrade would have just taken something that was defined in your TOML as a star because it had not yet gotten resolved, and it would actually instantiate that to a particular resolved version. And so the double command of Pixie add is essentially a no-op because it had already done the thing you was asking.
Yeah.
Okay. So I think we've reached that solution is done now, right?
Yep.
Okay, so I think we're going to take a 10-minute break, and then we're going to come back and take everything that we've learned so far to actually run some examples on Rev of actually using these tools and environments that we've been making and actually trying to run some code. So we've got
Yep.
10 minutes.
See you at 4:20.
I'm gonna get a drink.
Yeah.
Yeah, but I only do that because
So that wound up taking 45 minutes.
how long did we budget?
I think 45 minutes.
Heck yeah. I think you and Ruben are much better at accurate time estimation than I am.
It's mostly, I just assume it's always going to take longer than I think it's going to take. Yeah.
I totally agree. So maybe show some empathy here. I totally agree that
Can't laugh about action. Laugh at something. Not at all. Possibly. Possibly, yes. Yeah.
All right. Oh,
I think we got,
1 minute.
yeah, 1 minute.
Okay.
What did I do with my water bottle?
I remember it being here at one point. Oh,
Oh, brilliant. Thank you.
that's why we weren't tripping over it, so we didn't know where it was anymore.
So,
Yeah.
yeah, awesome job keeping the time, both of you. I'm very impressed. So,
Thank you.
yeah. Also, thank you for working on my machine because I can
I'm
appreciate
sorry
that.
for
Like,
being like a
no,
klutz.
no.
like-
You were doing great. I like if I was on your guys' machine, I would have somehow like faulted something by now. So.
I was like, great, I've disconnected from Brev in the middle of this. That was a mistake. I think I fixed it already.
Oh,
So,
yeah.
But that was also why I kind of like moved away from doing more terminal stuff. I'm like, I don't know how long this will take to set up. I want to move to like just,
Yeah.
Do you want to start it? Or?
Yeah.
That's fine.
Yeah. Let me. Yeah.
Oh, the other thing they were telling us was like make sure that we're saying the questions into the mic when people
Oh,
ask,
so
it
can
gets
can
a
hear
better
them.
recording.
Oh, okay. Sure.
Yeah. I know it's like the most unnatural thing to do this, and it's like very easy to forget. I've not been doing a great job of it either. I was trying to look for a mic at one point to see if we could have one in the audience, but it was too hard to find people. And there were enough other more pressing groups.
If it's okay with you, instead of going to the hardware acceleration, I was for time to make sure that we hit stuff. I was gonna do the ML, and then
Sorry.
and
Did I jump to the wrong bit in the?
just like one earlier because I wanted to make sure that we cover this so that if we were time limited, I'm gonna be like.
If anything, it's me looking at things in large font and like missing something and scrolling past it.
I mean, it's also weird because like you're seeing a kind of a very letterboxed view of things.
That's true.
Yeah. Okay, and then I forget. Did we? Oh, whoops! No, that.
The entire.
Yeah. Okay, so yeah, we didn't download.
Yeah. Oh, what was I supposed to do?
It's just at the very end we like download this bit of code just to show we weren't lying to you. We actually did this.
Yeah, I sped through this because I felt like we were already running late.
Yeah.
Sorry.
Why are you being slow? Okay, there we go. Cool. Yeah. Okay. We are going to reconvene for kind of the last bit. So Reuben and John have done an awesome job of actually like getting us to this stage and also keeping to time, which is kind of awesome. So I'm going to now kind of take us from setting this up to now getting to run some code examples. So the one thing that we didn't do at the very end is we found that we were on Brev with these GPUs, and we also in our if we look inside of our TOML files, we have CUDA environments, and we have if I do if I look at the TOML file again, we also have, for the Linux 64, we have PyTorch GPU. So we can do pixi list PyTorch, and we see that we have PyTorch GPU, but we haven't kind of done a proof of principle that all this stuff actually works together. So we should do that by running some code. So if you go to the very bottom of the what's the name of this section? The introduction to CUDA conda packages. So if you go on that and go to the very bottom, or just before the exercise, then we have this bit here about this code chunk, which is called a suggested file name of torch detect GPU. So if we copy all of that into our clipboard, and then we can use your favorite text editor, torch detect GPU.py. And if you dump all that in, and if you check to make sure that there's something there you actually wrote, then we can now we should now be able to run we should now be able to run this. So, and as a reminder, to activate your environments with Pixie, you either do something like Pixie shell, which drops you into a subshell and activates the workspace environment, since you're down in a subshell, if you type exit, then you exit that subshell and come back up, or you use Pixie run, and Pixie run will activate whatever environment is default, or unless you pass it a particular one. And then anything that follows Pixie run will be executed in that environment. So in this particular case, we're going to do Pixie run Python torch detect GPU. And so it activated the environment, and it ran using PyTorch code, and it's showing us that the build of PyTorch that we have was built with these CUDA versions, that it is fine, and that PyTorch can see a GPU in our system, and then it tells us information about that GPU, and it tells us that it sees the NVIDIA L4 GPU that we have. So this is good. So this means that we can actually start doing things with our code, our environments, and our hardware. So we're going to now move on to also check out some of these further resources afterwards. We're going to now move on to machine learning workflows with a Pixie workspace. So as oops, that's wrong turn, yeah. Okay, here we go. Yeah, sorry, I'm not used to seeing it so big, so I'm trying to navigate around a little bit. All right, so we've done all this work of setting up environments and learning how to use the semantics of Pixie. So now let's do some stuff with it. So we're going to run a, maybe everyone's first example machine learning workflow, maybe not the most exciting one, so mea culpa, but we're going to train a convolutional neural network on the MNIST dataset, which is, I think, probably the example that's in most PyTorch example, the first example out there. So we're going to do that, but for time's sake, we're not going to actually step through and write all the convolutional neural network code ourselves. We're actually going to use an implementation that I wrote myself earlier. So we're going to So we're going to go ahead and copy this. So this very first line, this is in version control, but for this particular instance, we don't need the full repository. We just need this example. So we're going to go ahead and copy this line to curl down this code. And then we're also going to place it in a particular directory just so that we don't lose track of it later. So we're going to make a source directory, and we're now going to move torch mnest under that source directory. Okay. All right, so we can reuse a lot of what we have already learned about, but we're now going to kind of extend what we just did, but we're now going to, sorry. Yeah, okay, sorry. We're under CUDA example. I wanted to do this one directory up, so we're going to do cd ... and we're going to move, we're going to, let's do mkdir -p src, and let's just copy under CUDA example src torch mnest. Let's copy that under our source directory just so that it's up and about. Okay, so we're going to remake another Pixie environment, and this time one of the dependencies, so we had previously installed PyTorch, the GPU version of it, but because we're going to be using a convolutional neural network, we're also going to use the Torch Vision library, which has building blocks for that as well as data sets. So these are the only important libraries that we're going to need to do this that aren't part of the standard library. So we're going to go ahead and pull those in. We're going to use what we've learned so far to take a 5-minute exercise to try and build a new Pixie workspace that is going to have PyTorch and Torch Vision in it. And we want to support CUDA 12. And then in this workspace, we want to have both a CPU version as well as a GPU version so that we can compare them. So let's also make sure that that in this workspace, we create an environment that we'll call CPU that has the CPU version of PyTorch and Torch version installed. And then we'll also make sure that we have an environment called GPU that has the GPU version of PyTorch and Torch Vision installed. So let's take 5 minutes and see if you can do that in that time period, and then we'll reconvene and run through that solution together. Yeah, I was trying to remember what I called it. So I'm going to, just to maybe make naming conventions easier for us, I'm going to call this, I'm going to use Pixie init to create a new directory with an instantiated manifest called ML example. Okay, so that might have been a quick 5 minutes, but that's been 5 minutes, and so we are gonna now kind of step through this together. So if you think you're almost done, then you can race me talking, and we'll see. But I'm gonna be a little bit slow because I'm gonna live code this. Okay, so we, like I said, here I'll even really do this, so I'll destroy my ML example. So we're gonna create a new workspace. So I'm gonna create a new, I'm gonna do pixi init ml-example. And so we've, created a whole new workspace directory. So I'm now gonna cd into ML example. Okay, so now that we've done that, so one of the reasons we add multiple platforms is because we want to make sure that even though we might be targeting a platform that we don't have or our colleagues might not have, so like for example, you're working on Mac OS and you want to be targeting Linux 64, you add additional platforms, you can add additional platforms outside of the target platform so that people can still actually develop and solve on those platforms if you're using conda packages. So the first thing we want to do is also add the different sorts of platforms we want to support. Here, for these example purposes, I'm going to add what I call common ones, so Linux 64, Mac OS, Apple Silicon, which is ARM 64, and then Windows 64. So we can do that using Pixi, Workspace, Platform, and then also remember you always have the handy help command to get more information. Add Linux 64, OS X, ARM 64, and Win 64. We added those platforms. If we take a look at the TOML file, then we see that we got them. All right, so we also know that across both of these platforms, we said we wanted to make a CPU feature and environment and a GPU feature and environment. We know that we want Python for both of them, and Python doesn't have a GPU version of it, right? So we can say that that will be a common dependency across them both. So we can use we can just go ahead and do pixi, add Python, and install that into our default environment. And then we can build features that extend that default environment to get the ones that we care about, to get the particular things we care about. So let's first add those CPU requirements to actually get the feature we want for a CPU. So we're going to say pixi add feature. We're going to call it the feature CPU, and we're going to add both PyTorch CPU as well as Torch Vision, and I believe that's all that we need. Okay, so that went ahead, we got those. And then now let's go ahead and create, so that was our feature. Remember, features are these Lego-like building blocks that we can use to build up things. So if we look at the pixi.toml, we have now this feature that we've gone ahead and defined that we need these things, but you'll also notice that it's currently a star. It's not resolved to any particular versions because we said we want these things, but since we don't have an environment for them to live in yet, they haven't actually been instantiated to any particular version. We've more still just had them as a declarative element. So let's actually now add these, let's add an environment that uses this feature. And we'll do this by doing pixi workspace environment add, and then we need to tell it which features, if any, we want. So we're going to say feature CPU, and now we need to finally name this environment, and we're also going to name this environment CPU. Okay, so now if we look at our TOML file, we now see that we've got an environment there, and that it's named CPU, and it takes as a list of arguments features. One of those is our feature CPU. Okay, so we can now also, but we still have these PyTorch CPU and Torch Vision dependencies as just star, these uninstantiated versions. So we can actually now do something about that because we've actually defined an environment. So we can now say pixi upgrade, and we can say what feature we want to upgrade, and we can say CPU, and this is now actually going to try and instantiate and lock those. And if we now look at the TOML file again, we now see that these have actually resolved to particular versions. So we now said that we're going to get PyTorch version 2.7.1 and Torch version 0.22. Okay. All right. So we now have we have an environment. We have a feature and an environment for the CPU stuff. Let's do that for GPU now. So basically the exact same sort of workflow. We're going to, again, make sure that we define our system requirements of CUDA. So we're going to do pixi workspace system requirements, if I can spell. And then we're going to add those to a feature called GPU. And we're going to specify that system requirement as the CUDA virtual package, and we're going to say we want that at version 12. Again, looking at what that created for us, we have now a feature called GPU that defined a system requirement, which is our CUDA virtual package version 12. Also, if you tried to do this on a machine where there wasn't the CUDA virtual package, and that would be present if NVIDIA drivers were detected, you can actually you can basically say, I know better, and I'm going to override this to still be able to solve things as if that virtual package was there by using this export conda override CUDA 12 export CUDA override conda override CUDA equals 12, which basically sets the same information internally as if you had that virtual package. So it allows you to actually solve for CUDA dependencies, even though you might be on a machine like a Mac OS machine where you don't have a CUDA system. So this can be really useful, and we'll actually see this later on with Docker containers, where we can solve environments or solve or install environments where there isn't any CUDA drivers yet, NVIDIA or CUDA drivers yet, by using this little export command. Okay, so we already have a feature, and we already have our system requirements. So yeah, so now let's go ahead and create an environment from that. So we can do pixi workspace environment, add feature. We're going to build that environment from the GPU feature, and we're going to call that environment GPU. So once again, we now have a GPU environment that is being built from the GPU feature. And now we can also say, let's now get our PyTorch and PyTorch GPU and Torch Vision dependencies, and we want that for the particular target platform we care about, which is Linux 64. So we're going to specifically target that for this GPU feature. So we're going to say pixi add -- platform Linux -64. And we're also going to say we're going to add this to our GPU feature. And now we're just going to give the dependencies, which in this case are PyTorch GPU and Torch Vision. We're going to hit add. You can see it's solved and locked. It's updating the lock file. And it's also using the fact that we have these previously installed versions cached, so that was really nice and fast. Okay, so we are basically there. So again, so we're now going to, let's CP from above us the source directory. Let's copy that locally. So now inside of this, if we now look at the directory structure, we have our pixi manifest and our lock file, as well as the pixi directory that has all of our environments underneath it. And then we also have the source directory, which has our code in it. So we have the source directory contains our torch MNIST code, which is what we're actually going to use to train. And so let's first, as kind of a comparison between the CPU and the GPU environments, let's now run that code with this information that we have here. Let's just copy and paste it to avoid kind of spelling everything out, but let's run it in the CPU environment. So if we do pixi run environment CPU, Python source torch MNIST, and then we give it some additional information as command line flags, if we hit enter, then you can see that we're actually installing the environment that we actually had locked, and we're now starting to execute that code. We downloaded the data set, and we are starting to train. This is a little slow, though. So you're kind of hoping that this would be flying by a little bit faster. We're only also 25% of the way through one training epoch, and this is not super impressive. So actually, let's bail on this because that's going to take a little bit of time. We're on Brev where we have nice NVIDIA GPUs, so let's actually use a different command, and we're now going to switch the environment we ran in from the CPU environment to the GPU environment. And you could just go up in your history and edit things, but I'm also going to change the number of epochs that we're going to train for from just 2 short ones to, let's do 14 or 20 to actually try and go do more training runs. So if we now copy and paste that, then we're making sure that we get the versions of libtorch and CUDA and such. So that's going to take, okay, we've got a couple more seconds to actually download everything from Conda Forge. So that downloaded, and now we're starting to train. And we're seeing that things are going quite a bit faster. We're only maybe 5 seconds in, and we're already at 50% of the way through the first training epoch. So all right, raise your hand if if you are currently not training a GPU. Or training a neural network on a GPU. Okay, so we have some people who are behind us a little bit, so let's go ahead and see if we can catch people up to speed while our network trains. Oh, okay, yeah. If you're still waiting for the CPU to finish, just like bail on it because it's slow. So go like. Yeah. I mean, you can do whatever you want. You are your own person, but we showed you the CPU version because it's boring and slow, and we then wanted to show you that GPUs are fun. Okay, hopefully people have GPU going burr. Seems like it, so we're almost there.
Very common mistake I see by less experienced kids. And they're not help that yourself.
Does anybody need help? Everything's going smoothly?
Okay, so that just finished training. Hopefully it did for you as well. Again, this is a very simple example, so we shouldn't be necessarily expecting things too crazy. We also want something that would actually train in under a couple minutes. All right, so we went ahead and ran some commands manually. That's fine. But as Ruben also mentioned, we have this task system that's built into Pixie as well. So let's now also add tasks to the CPU feature and the GPU feature that are train CPU and train GPU, so that in the future, instead of having to remember what were the individual like flags and different metadata that we're adding to the commands, we can just run Pixie run train GPU and we could rerun the same workflow. So let's take maybe like 2 minutes to try and do that as an exercise. Also, while we've been teaching you the command line interface to add different things, that's partially because we're running a tutorial and it's nice to be able to see exactly what people typed into their terminal to be able to debug things, but there's also nothing keeping you from just editing that Pixie TOML file yourself. So you should feel free to like treat it like any other configuration file and open it in a text editor and manipulate it as you'd like. So that's usually how I'm actually interacting with the Pixie manifest, is in my text editor, not through the command line. Okay, so that was 2 minutes. So, so the way that we're going to do this, as Reuben showed earlier, is that we're going to use the pixi task add command line, and then we'll tell it using the features flag, we'll tell them where we want to put things. So we'll do pixi task add feature CPU description is train MNIST on CPU, and then what we need to do is that we need to actually give the name of that task, which we're going to call train CPU, and then in quotes we're going to give the actual command, like full command. So here I'm going to just copy and paste, and so I'm actually going to cancel that out. Okay, so now it says, oh, you've added this, and so if we again look at the TOML file, then we can see that we now have this under the feature.cpu tasks. We have a task that has that information. And so we can do the same thing, and for time I'm just going to copy and paste, but for the GPU environment. Is that, oh, I copied the wrong thing. Okay, yeah, so now I've added a train GPU, which is now adding the command that we ran to train the GPU instance. So if we again look at the TOML file, we now see that under our feature CPU tasks, we have the train CPU, and if we look under feature GPU tasks, we have train GPU. And then since we've added tasks, we also now have ways of interrogating what's actually in this workspace. So we can say pixi task list, or is it? And it now it now gives us information about the different tasks that are available, as well as the descriptions that we gave. And so that means if you're dropping into a repository that is a Pixi project, if you clone that down and enter it, then if you want to understand what are the tasks available to you and maybe what those things can do, you can just run pixi task list, and you can get a quick summary over everything that that the developers might want you to be able to do. There's also usually a canonical start task, which basically you can run pixi run start in most Pixi projects, and that basically is a kind of a way for the project developers to say, hey, I think if you're checking out this project, you probably want to do this, and it will then launch whatever that is for you. Okay, right. I'm going to skip the subtables bit. That's just more of a visual thing. I'll also note, though, that we remember that train CPU and train GPU, these existed in particular features, and those features exist only in one of the two environments we have. The train CPU only is defined for the CPU environment, and train GPU task is only defined for the GPU environment. But if I run pixi run train GPU, then you'll notice that it just works. It just starts running. But I'm going to cancel out from that. But you'll notice that I didn't actually tell it that I needed the GPU environment active or not. And that's because Pixi is smart enough that if it finds that a task name is uniquely defined in any one particular environment, then it already knows that, and it doesn't need you to tell it which environment to activate. And so it will intelligently figure that out and do it for you. If I happen to have just tasks that were called train, so if in both the CPU and the GPU environment, if I had tasks that were called train, and here I'll actually demo that. Yeah, so let me get rid of the train GPU and train GPU. And now they're just called, so now if I look at Pixi task list, I just see that I have, Oh, oops, did I delete something? No, okay, so, yeah, so, so I've now defined it so that there's ambiguity in the task name. So if I now say pixi run train without specifying the environment, then it says, hey, I actually found 2 of these, which one do you want? And so it won't guess for you and potentially cause you to run the wrong workflow. You can tell it which one you want, and it will go ahead and start off for you. But this is also maybe a good motivation to use, in the same way we want to have descriptive variable names in our code, you should probably also have descriptive task name in your tasks so that you can make it nice for both you, your users, and Pixie to try and resolve those sorts of things. All right, so we went ahead and trained a machine learning model, so that's cool. But at the same time, normally we kind of like stop at these points and we go on to something else. But I'd like to actually go a little bit further and actually say that, well, we trained a machine learning model, we should actually do something with it. And so maybe we should actually do prediction. We should use it to do ML inference. And so we'll cheat a little bit and not go and find some novel handwriting cases. We'll actually just reuse the examples that exist in the PyTorch Vision or Torch Vision dataset. But we're going to use some code that I've written that will actually use this model that we trained to try and actually make a prediction about some data. So let's first actually get that code. So let's curl that down using this command right here. And so now we have this torch mnist inference Python code. And let's move that torch mnist inference Python code under source. And then we can maybe also take a look at that code as well. So we can basically see what's happening is that we're just loading some Python libraries. We are defining the same neural network architecture that we actually used while training so that we can we'll be able to load the network, the trained model into an actual network class. We're defining some pre-processing and prediction functions to actually be able to take the images that are in the data set and do something with it. And then we also define some argparse arguments to kind of help us out. But the bulk of what's happening is that we're going to actually select images that we would like to try and make a prediction with our model about what the handwritten number is. And then we're basically just loading in the machine learning model from our trained model and making predictions. And when he said, if you asked what's the trained model, we asked to save out our PyTorch model as this mnist_cnn.pt, where PT is an archive that actually contains both the machine learning model as well as the weights. Okay, so we have things right now in so we have this CPU and GPU, but these are our training environments. But we now, if you actually also look at the head of the torch mnist thing, or Python code, then you see, oh wait, there's matplotlib that's being pulled in here because we want to be able to do some image manipulation as well. But we don't have matplotlib installed so far. And it doesn't actually make sense for us to require matplotlib in our training environments because we aren't using matplotlib to do anything there. So there's no reason for us to add all that in. So as another, let's say as a 2-minute exercise, let's now create an inference environment in this existing workspace that we have that is going to use the GPU feature. So we're going to reuse that Lego building block of the GPU feature, but then let's also now define an inference feature that will have the missing dependencies of matplotlib, and then from those 2 features, let's create an inference environment. So let's try and do that in 2 minutes before we go over the solution. Yeah, we're not gonna make the containers, but that's totally fine. And I'll like announce that and then be like, come find me and we can go through it. But yeah, no, like we should definitely close with that. Yeah, and just like show people that. Yeah. Okay, so that's been 2 minutes. Also, as a quick heads up, since we have 20 minutes left, we're definitely not going to cover building Linux containers and using GitHub Actions and GitHub Container Image Registry, and then actually, pulling that down and Docker and all that stuff. So that was maybe a little bit ambitious, but if you want to talk about that later, we definitely can. But we're going to try and keep things a little bit more simple for the next 20 minutes. So let's kind of run through that solution real quick. All right, so we said that we want a new feature. We want to make a new environment that builds upon the Lego building block of the GPU feature, but also uses a new feature called inference. So let's create a new feature called inference that is going to take matplotlib as a dependency. So we can do pixi add feature inference, and then we're going to say we're going to add matplotlib. Okay, and since we've already installed it once, then it was basically a trivial solve there. Oh no, sorry. It's because we haven't we defined a feature, but we haven't instantiated that into an environment. So we basically said, I want this, but we haven't actually done any solving yet. So that's why it was instantaneous. But as we said, we now want to have an environment that uses both the GPU and inference features. So let's do that. Let's do pixi workspace environment add, and we need to define the features. So we're going to say feature GPU, and then also feature inference. And then we also said we wanted to call the environment inference, and so we need to actually finally give this environment a name. Okay, so we add that environment, and again, if we look at what's actually there, then we see that inference takes both GPU and the Lego building features of GPU and inference together. But we still see that matplotlib is uninstantiated. So we can optionally say Pixie upgrade feature inference, and it now will actually do the solves based on the constraints and install that. And now if we look, then we see that we actually have a particular instantiated version. All right, so that now means that we are basically ready to go because we've defined our environment, and we're able to super trivially do that by just basically saying, I need one key piece on top of this environment that I already, this environment component, this feature that I already defined, and now everything's installed. So now if we copy and paste this line, we're now going to run that inference code in this inference environment. And I'll clear my screen. So so quickly we're just going to say we're defining a model path. So where should we look for the model that we're actually going to be using for inference? And then we're also going to define an output path for, or we're also going to define a path for a particular image. And in this case, that we're going to try and do prediction on. In this case, that path doesn't exist, and so since we're using this toy example and we know that we have access to the Torch Vision data set, it's going to then go and pull from Torch Vision. So we went ahead and so it now says, oh, I found a 4 and or I was given an image, I made a prediction, and in this particular case, because we didn't actually have an image yet and we just went and pulled something from the test data case, we were able to actually check to see what it was. But you'll also note that we now have written out this test image to disk. So we now actually have an image file. And so if we were to rerun that again, and you could now imagine that this would be any handwritten, an image of any handwritten number, then it's going to go ahead and run again and think, and it makes a prediction. And so in this case, we were just giving it an actual image. And so it doesn't know we don't actually have the labeled data for it, but we were actually now able to use this trained model to actually do something and to make a prediction about this image. And we were able to do that super trivially by just extending the features that we have defined in our workspace pretty quickly. All right, so another thing that I think is important to kind of mention, oh wait, I'm not in a Git repository at the moment, but right now we've just defined some code, and we also have just have this Pixie manifest and this Pixie lock file. You could imagine that in any sort of, so you can imagine that if all this was in a version controlled repository, you could now clone all this down, and so if a colleague has done this work using Pixie, then they can just give it to you and say, hey, you should check this out. And without having to know anything about the environments or anything about how it was made, they can say, oh, just run, when you get it, run the Pixie train GPU task, and you can, and it would, with the existence of the lock file, instead of having to resolve an environment, it simply just says, how fast is your internet speed, and pulls everything down to be able to get the exact environment you need solved. And so we're not going to clobber this entire directory and show that by like cloning totally fresh, but what we can do is we can run Pixie clean. And Pixie clean literally did just clobber your environment directory. So if you look under the .pixie directory, which actually contained all the directory folders for your environments, they're gone. You literally rm-rf them. But because, as we mentioned, Pixie's been caching all of this, we're not now. If I say, if let's go up again and let's say, hey, I don't have anything installed, but I'm going to run this command to do model inference. It's going ahead and installing all this, but it installed literally the entire directory system and everything from cache in like 2 seconds. So this is also powerful because it means, so we just so people go ahead and do this, like actually run pixi clean and rerun that command. And you can show for yourself that under Pixi, there's, under the .pixi directory, there's now an ems directory and an inference directory. And there's a full directory hierarchy here that didn't exist a few minutes ago, and you were able to completely get it back at bit for bit at the hash level after we totally deleted it. And so you can imagine that the exact same thing works if you're cloning a totally new repository. And here we were taking advantage of the fact that we knew that we just installed all this software, and so we knew that it was already in cache. But let's say that you're working with your colleagues and and so maybe you already have been working on a similar project. With Pixi, those files might already be in cache for you already. So the time to be able to go from downloading a totally new repository that you've never used before to using an exactly locked Pixi environment to be using hardware accelerated workflows could literally be 5 seconds. And that's something that's, I think, really we couldn't do just like 2 years ago. But thanks to both CUDA packages and Pixi, we now can. Okay, so we've got 10 minutes left. Also, this is a little disclaimer that in the real world, you're probably not writing your own little inference script. You're probably using something like NVIDIA Triton server, and that's like a good thing to do. But this is a tutorial with small examples. So don't try and actually take this to your real world examples. But we're going to end with kind of going beyond these simple machine learning examples to also show you the fact that this is not just machine learning, but CUDA, and that there's CUDAs many different places. So I'm going to hand it over to John to kind of finish this segment out, where we're going to show you some of the other CUDA accelerated libraries that you might already know and love, and how we can kind of use those quickly.
Thank you, Matthew. Yeah, as Matthew was saying, I'm sure many of you have heard of CUDA in the context of deep learning, but have you heard of CUDA in terms of arrays? Can you raise your hands? Okay, like a handful of people. What about with data frames? Graphs? ML? Okay, so like little scattering of people throughout the crowd. So I just want to point out that you can do a lot of different parallel operations on CUDA. So with arrays, CuPy is a good library to start with. This looks a lot like NumPy. How many people here use NumPy? Yeah, okay, so that's definitely everybody, right? So CuPy is the same thing. You can create arrays in the same way. Just as we've been creating workspaces, we can create a workspace with CuPy. So this uses CUDA 12 and 13 for CuPy in a Python 3.13 environment. We've created a NumPy array here. And you can create a CuPy array. Any difference? Looks the same, right? The only real difference here is what we've imported. And then if I want to compute the norms of two arrays, I do the same thing, and I get the same results at the end, right? The only difference is, in one case, it ran on the CPU. On the other case, it ran on a GPU. Now, admittedly, these are very small arrays. So in reality, you probably want much bigger arrays to really get the value of using a GPU. But this is something you can certainly do. And CuPy is a great library to do that with. Additionally, NVIDIA works on the Rapid stack. CUDF in particular is the data frame library. And CUDF can do a lot of the same things that if you're familiar with pandas. Anybody use pandas here? Yeah, again, basically everybody, right? Okay. So CUDF works the same way. Again, we can create an environment with CUDF. And we can grab a little bit of CSV data. So this is data that comes from Wikipedia. And you can run this yourselves. And you can download it with pandas. And then you can download it with CUDF. Same instructions in both cases. Just in this case, now it's in the GPU. And then you could go through this and do some kind of simple operation, like compute how many pages on Wikipedia use a particular language, like English or French or Spanish. And similarly, yeah, and you could look at other statistics or information about them. Additionally, Rapids has libraries QML, which is similar to scikit-learn. So if you're familiar, anybody here use scikit-learn? Yeah, again, basically everyone. So if you're familiar with scikit-learn, QML is very similar and works the same way. Anybody here use NetworkX? Few people? Okay. So cuGraph does the same kind of thing on a GPU and has a similar API. So again, you can do a lot of different operations on the GPU. Doesn't need to be just deep learning. In reality, we all have data of some kind. We need to load it somehow. We may need to clean it up first. We may want to do some kind of aggregation or consolidation of this data before we work with it. We may get results on the back end that we actually need to work with a bit more. So all these different tools can be combined together to give a thorough working of your data on GPU. Any questions about any of that? No?
So we've kind of been skipping these further references, but given that like CuPy is developed by a team, but the whole Rapids ecosystem is developed by NVIDIA, and one of the things I want to shout out is that NVIDIA has this accelerated computing hub, which is a open source GitHub repository from the members of the NVIDIA open source team that basically is a curated collection of different examples of how to use different hardware accelerated tools that aren't things like your typical machine learning libraries like JAX or PyTorch. These are using the whole Rapid stack as well as things like CuPy. And it's is updated on a somewhat regular cadence to also include lots of examples. So if you're interested in trying to think about how can I use CUDA to be able to accelerate my data science workflow, then that's a great place. Maybe also there was 2 tutorials that happened by members of NVIDIA this morning that involved both the bits of CUDA and CUDA Python, as well as the Rapids stack itself. So maybe some of you were there and already got a taste of it, but if not, be on the lookout for when those tutorials are posted, both in terms of their materials as well as when those videos go online. And then also there's the Rapids documentation also has lots of examples as well. So we were pretty brief here, but there's lots of resources if you're interested. As was mentioned, we didn't have time, but the kind of closing bit here was we were going to show how, given the way that Pixie works, it is a really great and kind of natural partner for containerization in the sense that it makes it trivial for you to be able to install environments they already have solved into Linux containers that, and then use Linux containers as deployment technologies to then go run in particular places that might be perhaps like internet constrained or might have additional security instances or are optimized for containers themselves. So we're not going to cover that today. However, we do have basically a whole workflow here. So if you have questions, come find any of us this week. We're more than happy to chat about this. And also, all of this is publicly available, so you should be able to run through this yourself. And this last section we're skipping would have you actually take those the GPU environments that we created, containerize them in or write a Docker file that would describe how to containerize it, use GitHub Actions to be able to build that container, publish it to your own personal instance of a GitHub container registry, and then be able to then pull down that container onto Brev and show yourself that the exact same code that you ran locally with Pixie, you could then run also using the NVIDIA GPUs in a Docker container with that containerized environment. We're going to skip that because we have 2 minutes left, we're going to close by just kind of announcing different things that we, as a team of instructors, have going on that you might be interested in, and also where to find us. So I'll start because I'm already blabbing. But so this, I am going to be running a 3-day extended workshop that covers similar things here at the University of Wisconsin-Madison the second week of August. This is a free workshop if you can get yourself there, and if you're a student and potentially interested, we have lodging support. So come talk to me if you're interested, and all of that is an open source course, which is supported by both the UW-Madison Data Science Institute as well as the University Research Software Sustainability Institute. So if you're interested, all that will also exist as an open source course, as kind of an extended version of this 4-hour tutorial. And I'll let Ruben talk next.
Yeah, thanks all for joining this this workshop. I hope you liked it. I would like to quickly mention that Pixie itself, where you've learned a lot about it today, it's a completely open source project, so feel free to go to the documentation, go to the GitHub page. If you have any issues, we hopefully can help you through those. But if you're like even more interested in joining our community, there's also a Discord link somewhere, not here of course when you try to show it. But we have a Discord that we have built a good community on currently, where you can definitely join us and ask more questions. Currently, it's so big that I don't have to answer all the questions anymore like I used to do in the first year, but there is a nice community that can help you with any of the issues that you might have come to today, and definitely hope you join there. And if you're interested in a little bit more information, like this is the basics of Pixie, but there's a lot more going on. We'll have a talk on Tuesday, me and my colleague Wolf, on the next steps of what Pixie can be used for, mainly building packages and whatever beyond that. So feel free to join that talk as well. And then, yeah, thank you for joining. And then I'll give the word to Sean.
Yeah, so we have a number of different talks from NVIDIA here at the conference, and a number of folks from NVIDIA. If you are from NVIDIA, could you raise your hand? So there are a few of us around. There's even more outside this room, and people coming on Wednesday after tutorials. We'll be around throughout this week, happy to answer questions, happy to talk about any of these things. I may not know the answer to everything you might ask, but I should be able to find somebody who can help answer your question. So, anything else? Oh, yes, please grab stickers. You've worked very, very hard. You deserve a reward. They're very beautiful stickers. Yeah, so round of applause for everyone.
Thank you.
Thank you.